Hi, my name is Corey Stennett, and this is my solution for homework 10-1. I'm going to have to move kind of quickly here because I reached the max time on Screencast-O-Matic, which is 15 minutes. Okay, so starting off, we have our custom linked list class. Normally we wouldn't have to do this because someone has already made it for us, but this is a test of how we understand how to iterate through and manipulate data structures. So linked list E means that it's a linked list that can take in any type, any class type, data type, whatever. Inside of that class, we're creating our inner class node, which is each individual instance of data within the list, and its pointer to the next item in the list. Okay. We have our constructor for the node, which sets the data equal to whatever data we want, and points to the next item or next node in the list, which is very important. It has to do that. And the no argument constructor for node sets both the data and the next equal to null. We create then, now that we have our inner class made node, we can then create variables or objects, node objects. And for a linked list, we have to have an empty head and tail. And here we've created the empty head and tail, made them null. This is our empty linked list now. For size, this I took from the book, essentially, because it works, so why not? You start off with a counter, which is 0, and then a position in the list, which you always start off with a head. While the position is not equal to null, we iterate through the list by going to the next node in the list using mNext. mNext gets to the next node. And then setting it equal to the current position, and then adding to the count. Once we've gotten to null, that means we've hit the tail. We count one last time, and we return that count to get the total size of the list. Okay. For add index element, while the list has an index high enough, this method takes that index and places an element to the list there. If it does so by looping to the current index, which requires hopping between nodes, replacing the most recent node with the element desired. So basically, if it's out of bounds, we throw this exception, which you're going to see a lot. If it's the head, then we're just going to use add first. If it's the tail, we're going to use add last. Add first and add last are methods I'll cover later. Basically, it adds the element that we want to the front of the list, makes it the head, or it makes it the tail. If it's not the head or the tail, then we're going to create our counter. We're going to create a position or front, which starts at the head, and then a most recent node that we've been at, as well as the node that we actually want to create. Okay. Then we're going to iterate through, counting as we go from front to the next item in the list. Okay, we're iterating through the whole list. The most recent is going to be equal to the most recent thing that we're on, and then that most recent thing is going to become the next thing, right? So we're going to be able to remember those once we hit the index, and then we're going to make the new node equal to that front node where we stopped, because that's exactly where we want to add it. That's the index where we stopped and we want to add it into. If that all succeeds, then we return true. For add, this is the same thing as add last. It said so in the instructions, so the only thing that's different is we return true here because it's a Boolean, whereas add last is a void. So we just return true and we use add last element. And that's pretty simple. I'll explain add last because it's a little more complex in a second. For add first, I used the book. And they had an example there which was head equals new node element head. But instead of head, we have this, so yeah, we're using imhead instead of head because imhead is the node object that we've created. And then we're using the node constructor to create the element at the head. And so add first actually ends up being kind of a simple thing because we're just putting something at the front and then pushing everything else back. And that's how that works. So for add last with a parameter element, if the list is empty, make the head of the list using the get element. Otherwise, adds the element to the end of the list. So if the head is equal to null, and this is necessary because of the code that, to come, if head is equal to null, which means the list is empty, then mHead equals new node element null. And that means we're making the head equal to this element and having its pointer set to the tail, which is null, which is correct. This is how you do it. It's kind of the same thing as up here, except we're pointing to null because we know that this is an empty list. Otherwise, if it's not an empty list, we have the new node equals the head, and while the I should have done position here. While position is equal to head, position, and while the next position is not equal to null, the new node, or position equals position next, so we iterate through. And then as soon as we get to the end of the list, right, so it's not equal to null, which means we're going until we hit the tail. But once we hit the tail, we're going to force it to go to that null value, the tail, m next. And we're going to create a new node there, referring to the element in the parameter and creating a new null pointer. This is the new tail, basically. Okay, so that's how add last works, and as I said, it goes into add, because add, all we're doing is putting it at the end of the list, so it does the same thing, but it returns true. Okay, for get, we have, as long as this is in bounds, it'll return the element of a particular index. So if it's not in bounds, it'll fail. If it's the head, it returns the data at the head. If it's the tail, it returns the data at the tail. Otherwise, now we can create our counter and our position, starting at the head as usual. We count through to get to the particular index. Once I reaches the index, we can stop this loop, and that means that the position that we've been iterating through the list will be equal to the position that we're looking for, the element at the position that we're looking for. So this position m data would be that element of this index. Okay, for set, we have kind of the same thing. I should have done a method here to cut out on some of this excess code, but that's okay. So for set, we take an element, place it into the position desired, if that position exists. So if it's not in the, if the list isn't big enough, we just throw an out of bounds exception. And we also have to return the data that we replaced, so we have to create that variable. If it's the head, we make the variable replaced equal to the head data, and set the head data equal to the element. Same thing with the tail. Otherwise, we iterate through, once again, position equals head, I equals 0. We're going to get to that particular point in the index that we wanted. We're going to make position equal to that, and then we're going to make the variable replaced, the thing that we're replacing, equal to the data at that position. And then we're going to make the data at that position equal to the element that we want set there, and then return the replaced element. Okay. For index of, this is a simple one. We use a counter to find the index, looping until the first instance of the element is found. If nothing is found, it will return -1. So we have our position front at the head, and our 0 index, our counter. While the front is not equal to null, is not the tail, basically. So while we haven't gotten to the end of the list, if the front data, or if the current data equals the element that we're looking for, return the index. Otherwise, keep counting up and raising that index and going from list node to list node in order. So front equals front next is going to the next. If we never end up returning an index, we just return -1. And that's how that works. Here contains, we have a case to reuse index of here. Basically, this contains wants to tell us if the element exists in this list, and index of does that already. So if index of element is greater than -1, return true. Otherwise, return false. Okay. Remove. As long as the index given is in bounds, this will remove the node at the current index. So we have the index. If the index is out of bounds, we do that. if the index is the head, we set the element, we set the element equal to the element at this index, which is the head, 0. And we use the get method that we made before. Okay. I'm not going to show that, I'm sorry, I'm out of time, but I already showed it before. Okay, so we make that element equal to the element at the head, and we make the head equal to the next item in the list, and we return the element. Okay, so if the index is at the head, we take the element at the head, we take the data at the head, so we can return that, and then we set the head equal to the next thing. It's basically just making it so that that first item doesn't even exist anymore, and the next thing is now the head of the list. Otherwise, we have to set up our counter, our position at the head, and then our most recent or previous equal to null. We iterate through until we get to the index, making the most recent equal to the current position and the current position equal to the next. Once we get to the end, or to the position that we want to be at, we remove the element at the position by linking it to the previous node, and then we return the element removed. Okay, so that's what this does. For remove with element instead of remove with index, we can actually use index of. So if index of is not equal to -1, we can remove index of element 1. And what this does, this index of element 1 is remove index of element 1 is reusing remove from here, remove an index. So we're removing whatever index or whatever element is at this index, right? And that works. Pretty nifty, and it cuts down a lot of the code. Return true if it works, otherwise return false. Clear just makes an empty list again. So it's kind of like making the constructor for the linked list again. You just set the head and tail equal to null, and then everything's gone. So the toString, this will return empty brackets for empty list, or all of the lists inside separated by commas and surrounded by the brackets. So you can see here, string result equals the first bracket, and then we've got this is so we can iterate through the list. The position equals head, or front equals head, while the front, our position is not equal to null. If the next position is equal to null, so if there's a tail coming up next, we're just going to add the data of this current position to the string. Otherwise, we're going to add the current data of this, or the data of this current position to the string and add a comma. And that's how we get commas in the right positions, and not at the end or the beginning. Okay? And then front equals front index just iterates through, and once we get to the end, this list, or once we get to the end of this list, this loop will be done, and then we add on to our result that's been manipulated here with the last bracket. This also makes it so that if there's no list here, if front is equal to null, then we just have brackets, and we return the result as brackets, and that works. So moving on to the demo. I only have 40 seconds left, so I've already played it here, and I just want to show you the demo. We added steak and potatoes. So steak went in first, then potatoes. That made steaks at the beginning of the list, then potatoes. Then we added nachos and pizza. So we added nachos at 0, which means nachos went right before. Nachos went right before steak, and then pizza went right before nachos. Then we removed potatoes successfully. Then we removed the index at 0 successfully, which was pizza. Then we added guacamole. And then I tested a few other things here. And I'm about out of time, so thank you very much for listening. If you have any questions, please let me know in the comments. Thanks.